Welcome everyone, I'm David Böhme and I'm welcoming you to our tutorial on automated application performance analysis with Caliper, Spot, and Hatchet that I'm preparing together with Stephanie Brink and Olga Pierce. So what's this all about? Well, there are a lot of great performance analysis tools out there, but most of them are actually focused on analyzing single runs and like doing deep dives in there to find performance bottlenecks, but that's not quite what we're aiming for with this tutorial. So instead, we want you to be able to build automated workflows to collect performance data and enable performance analysis as a routine activity for HPC software development. So a good use case for that is actually performance regression testing. So in this example here, you see the nightly test performance of one of our large physics codes over a period of 5 months. And you can see that there are, oops, how do I skip this? Excuse me a bit, I'll have to figure out how I'm kind of getting back here because my Zoom controls are in the way and it doesn't let me do anything else. Well, let's try this. Okay, so this is the nightly test performance of one of our large physics codes over a period of 5 months. And you can see performance regression cropping up at one point. And then over time, you see how the performance of the code improves as the developer optimizes their code. So we find this incredibly useful. So our developers are quite happy to have these capabilities. And at Lawrence Livermore, we've created this software stack that lets you create these or lets you do this automatic performance profiling. So it consists of Caliper, which is our instrumentation and profiling framework, Spot, which is a web front end for analyzing and visualizing large collections of individual runs. And then there's Hatchet, which is a Python library that lets you do scripted performance analysis or also interactive analysis in things like Jupyter notebooks. So we're covering these three tools in our tutorial. So I'm going to start with Caliper and Spot, and then later Stephanie is taking over and introduces Hatchet. Okay. So are there any questions up to this point? So just let me know. Otherwise, if you do have questions, just put them in the chat and I'll have Stephanie and Piotr monitoring them and they can interrupt me. Okay, well, if there aren't any questions, let me just get started with Caliper. So what is Caliper? It is a performance profiling library, actually. So the idea is that it integrates performance profiling capabilities directly into a program. So that way, profiling is always available without separate setup steps or third-party tools that you need to use just to record a performance data set. So this simplifies performance profiling in a lot of cases and makes it easier for application end users in particular to use them. And also just lets us enable performance profiling whenever we need it. Caliper is also a common instrumentation interface. So it is a library that lets you mark regions in the code and lets you measure performance for those regions. And we can also use this instrumentation interface, not just for Caliper itself, but also export that to other tools. It has a bunch of profiling features for HPC applications. So it supports all the usual programming models like MPI, CUDA, HIP, COCOS, and has functionality like call stack sampling or hardware counter measurements and memory profiling that might be useful. So typical Caliper use cases include lightweight always-on profiling. So you can just print a summary report for each run that you have. You can use it for a lot of performance debugging tasks, so you can use it to, well, drill down and find performance bottlenecks. You can also use it for performance introspection. So you can actually query performance at runtime from within the program. It's not something we use much, but it's something that you can do. An important use case for us are comparison studies across runs. So that includes, for example, the performance regression testing use case or also things like scaling studies. And Caliper is well used or very useful for this purpose because it can automatically record program metadata, and it is easy to automate, and that's what we're focusing on in this tutorial. So Caliper fits into this ecosystem together with Spot and Hatchet. As I mentioned, Caliper is our instrumentation and profiling component. Spot is a web front end for visualization and analysis of a lot of runs, and Hatchet is our call graph analysis library. And you can use Caliper to create input data for Spot, and from Spot you can actually launch Jupyter notebooks that use Hatchet to analyze specific runs or even a group of runs. You can also directly create performance data for Hatchet through Caliper. It has specific configurations for that. But that said, you don't actually have to, all of these programs are actually standalone components, so you don't need Spot or Hatchet to use Caliper, and simultaneously you don't need Caliper to use Hatchet. So you can produce all kinds of different output formats with Caliper, and simultaneously Hatchet can also use different profile input data sets, for example, from HPC Toolkit. However, they do work nicely together, and they enable our ubiquitous performance analysis workflow, as we call it. Okay, so on this link here, I actually have a few tutorial materials. So in this presentation, I'm actually mostly focusing on just demoing Caliper because we don't have too much time to just do hands-on exercises and these kinds of things. But if you want to play around with Caliper, I encourage you to check out this tutorial material. So you can download it from GitHub. It includes Caliper and the supporting libraries that it needs and a couple of example apps, so you can go there, play around with it, and it also has all the materials that you need to use Caliper. Otherwise, you can find information about Caliper in the GitHub repository and its separate documentation page. And if you have any sort of issues or questions, just put them in the GitHub issues page or the GitHub discussion page, and you can also contact me directly if you want to. Okay, so any questions up to this point? If not, let's go into actually using Caliper. So there are basically 3 steps that we have to do to use Caliper. So first of all, Caliper is an instrumentation-based library. So we usually go ahead and put region annotations into our code. So there are macros for you to do that, or functions in Fortran. And well, these let you mark regions that we can then measure. So once we have those, we can enable performance measurements, and there are several different runtime configurations that we can use for that. So you can choose between lightweight configurations with very little overhead, or you can record more detailed information, or you can turn Caliper off entirely. So there are several ways to configure Caliper. So one would be actually a config manager API. So this allows the program to control profiling automatically. And the second option is an environment variable or config file where you can enable some of these Caliper configurations. Finally, we want to analyze our data. And to do that, well, depending on the configurations, you get several or different kinds of outputs. There are just simply human readable reports in some configurations, and other configurations produce profile data sets or files that you can then analyze with Hatchet or put them into Spot. So let's talk about these steps in a little bit more detail. So first, let's start with the region profiling. So as I mentioned, Caliper is an instrumentation API. That's actually what it started out as. So much of the functionality in Caliper is built around these region annotations. So there are a bunch of macros in C or functions in Fortran to let you mark regions in the code. So in the example here, we're adding this region called init around this do init function, and that will then show up in our Caliper reports. There's also a low-level API that lets you annotate, well, pretty much anything that you might want to include in a performance analysis. Now, these region annotations themselves don't really do all that much on their own, so we need to enable configurations to use them. But it also means they're relatively lightweight, so we usually just keep them in the code. Okay, so how do you go about instrumenting a code, and why is manual instrumentation actually pretty useful? So here's a couple of guidelines that you can use. So first of all, be selective. So we typically instrument only high-level program subdivisions, so things like kernels and phases in the programs. So these annotations are not meant to pinpoint performance bottlenecks down to the source line level, but instead they should give you a broad overview of performance in your code, or let you focus on a specific region. If you do need more detail than that, you can combine the instrumentation with other techniques like call stack sampling. It's actually an advantage of the manual instrumentation, especially for large codes, because you get very little clutter that you would get with just instrumenting everything. And it also reduces overheads that you might otherwise get. Second, be clear. So you can and should choose meaningful names for your region. So here we have a code example with a Raja construct that computes a dot product. And with Caliper, we can just mark this as the dot product region. And then in your profiling output, we know that this is the dot product and not whatever weird thing the compiler generated for this code. So the region annotations allow you to choose names that you as a developer, that are meaningful to you as a developer. And finally, you can start small. So just add a few region instrumentations, just like annotate main and a couple of high-level functions, and then go from there. So it's very easy to just add instrumentation incrementally. Okay, so now that we have our region instrumentations, we can start recording performance measurements. And the easiest way to do that is to use one of Caliper's built-in configuration recipes. We can choose these, or one way to choose these is the caliconfig environment variable. And the example here, we are using the runtime report, and that just prints it prints the time that you spend in each of our annotated regions, and yeah, just puts it on the screen. So in an MPI program, it will actually compute statistics over all processes, so you get the minimum, maximum, average time across all MPI ranks, and you also get this percentage value that shows you where in the code you spend most of your time. So there are a lot of different profiling configurations for all kinds of purposes. So we've seen the runtime report. There are also specific reports for loops in the program, or just for MPI functions, and more specific purpose configurations for event tracing, producing output for Hatchet, or producing output for spots. There's the Caliquery or MPI Caliquery program, and you can ask that to list all the configurations that are available. I'm not going to go over all of these in detail, but yeah, just know that that's where you find all your different profiling configurations. Okay. So a lot of these configurations can actually take additional parameters, and they enable additional features like additional metrics that you can include, or select output options. Like, for example, you can redirect things into a file. So in the example here, you see the runtime report again, and this time with a couple of more parameters where we're adding the mem high watermark metric, and write the output into, well, std out in this case. And the help function also gives you more information as to which of these parameters are available for each profiling configuration. One interesting one is MPI profiling, for example. So the profile.mpi option enables MPI profiling. That way, Caliper intercepts all the MPI functions, and you see the time spent in MPI. The same thing also exists for CUDA. So the profile CUDA option intercepts the CUDA runtime API. And you see the time spent in CUDA memcopy and CUDA launch kernel and so on. There's also an option to actually measure the CUDA kernels themselves. And that way you see the time that you spend both on the CPU and on the GPU in each of your GPU activities. Okay, so as I mentioned, Caliper is also a common instrumentation interface, and we can actually forward these annotations to other profiling tools. So tools like NVIDIA's Insight Suite or NVProf actually have their own profiling interface. It's called NVTX. And with this NVTX option, we can forward Caliper regions to NVIDIA's API. And that way they then show up in the NVProf output here, for example. So this works with a bunch of different tools. We have this for NVProf and Insight. We also have it for RockProf and VTune and Tau. And then, of course, you can analyze Caliper data with Hatchet. So there's going to be a much more detailed information about that in the second part of the tutorial. There are two configurations that actually specifically produce output for Hatchet, Hatchet region profile and Hatchet sample profile. The region profile just uses the Caliper annotation regions from the instrumentation API. Hatchet sample profile will actually use call path sampling to get you individual function calls. Both of them produce JSON files that you can then load into Hatchet. Now, a pretty unique feature in Caliper is the config manager API. So this is an API that allows you to control profiling from within the program. So the way this works is you can create one of these config manager objects, and then you can add configurations to it. So the config manager API uses the same kind of configuration recipes that we've used with the CaliConfig environment variable. So for example, you can use it to launch the runtime report. And then you can start profiling at any time in the program. You can pause profiling also. And in the end, flush output. So this gives programs a lot more control as to where they can do their profiling and how. And we found this useful, especially in some of our larger codes, where automated mechanisms are just less robust in many cases. It also allows us to use program-specific flags to enable profiling. So for example, we can now use command line arguments from the program to select a profiling configuration. And this can also make it more useful or more usable for application end users. Okay, so if none of the built-in configuration recipes in Caliper do what you want, you can also configure Caliper manually, kind of. So Caliper includes a bunch of different service modules that each implement some kind of profiling functionality, and you can combine and configure them in a very flexible way. So in this case here, what we're actually doing is we're recording unified memory transfers between a CPU and a GPU, and then map them to both source code regions and actually named memory pools. So you see exactly in which region you have been copying data from which pools to which other pool. This produces a trace, and we can then use Caliper's own query language to produce this report here. So I'm not going to go into all the details here, but just goes to show that, well, Caliper, you can use Caliper as a building block to build very specific performance analysis tools, essentially. So you're not even just limited to all the recipes that you already have, but you can essentially build your own. Now there's a whole bunch of ways that you can process Caliper output. So as I already mentioned, there are a bunch of configurations that just print human readable reports. You can write data into Spot, our web front end. Then there are a bunch of different ways to produce output for Hatchet. So there are the specific profiling configurations for a Hatchet. And finally, you can also use manual configurations or some configurations like event trace to produce Caliper's own native output format and then process that in many different ways. For example, with the Caliquery tool or a Python reader library that we have. And yeah, essentially from all of these ways, you can feed data into Hatchet. So arguably there are too many ways in Caliper to produce output for Hatchet. We're going to show you the most useful ones, I would say. But yeah, it's a very flexible approach. Okay, so that's essentially the first part. It's covered Caliper on its own. And next I'm gonna show how to record data for the Spot web front end and really enable the automatic recording of performance data and analyzing a large collection of runs. But first of all, are there any questions so far?
Haven't seen any in the chat.
Okay, thanks. If not, let's go on. So for Spot, we also follow essentially most of the Caliper workflow. So we add region instrumentations to our code that we want to see eventually in our Spot output. But in addition to that, we're also recording program metadata. Now, this is actually quite important for a lot of the analysis that we do. So we often want to compare performance between runs. So for example, take a scaling study where we want to compare data between different MPI job sizes or different numbers of threads. Or we want to study different build configurations, or we want to know performance with different problem or input problems. So for all that, we need to know which run was using any of these parameters, and we have a separate library to collect this information. It's called ADIAC. And just like we add a region instrumentation, we also add these metadata annotations manually in the code, and that way we can record this automatically and script all these workflows on top of it. So we're going to talk a lot more about ADIAC in the following slides. But meanwhile, while we have, once we have all these region and metadata annotations, we can just run the program with the specific Spot configuration to produce Spot output. We usually use the Caliper config manager API to control that, but we can also use the environment variable here. So once we run the program with the Spot config, it'll produce a Caliper file with the profiling and metadata in the end. You can move this to an experiment directory and then point Spot to this, and it will load this user interface that I'm also going to show you later. Okay, so let's talk a little bit about ADIAC. So ADIAC is a C and C++ library that we can use to record program metadata. And it has two kinds of calls. So there's a built-in functionality to collect common kind of metadata information, things like a username, program launch date, MPI job size, and so on. And there's also a key value style interface that lets you add program-specific metadata. So these would usually be some program input configurations and things like that, your problem size, or in this case here, in the example, the solver that you used. So typically the kind of information that we record includes environment information. So, well, the user launch date system it's running on and so on. It would be compiling information. So what compiler did you use? What compile flags? And then program configuration information. So the input problem description, problem size, and essentially any kind of program input that has some impact on performance. And we also often record some kind of global performance output or result variables like a figure of merit or the total wall clock runtime that you spend in the program. And that makes some basic performance analyses in Spot easier. Okay, so here's all the functions that you can use to record common kinds of metadata information. So it includes the username, user ID, executable path, command line, and so on. There's a whole bunch that you can just add automatically. For Spot, we'll need at least the launch date, which records the well, date and time that the program was launched. And we need that to essentially sort things by date in Spot. But the more you add, the more useful Spot can be. So then we have this separate set of functions that lets you record key value information, so program specific kind of metadata information that you want to record. There is a C++ and the C interface for this. The C++ interface just supports a lot of different data types, so it supports a lot of, well, most of the basic built-in types like integers, floating points, strings, obviously, but also a couple of containers, so you can put arrays in there if you want to. And then there are a couple of kind of special types like a path or a version number. There's also an interface for C that does the same thing, and this kind of works like printf. So you essentially give RDAC a key for your value, a data type with this %d description, for example, to record an integer, or a %s for a string. And there too, you can add additional data types like lists with these square brackets, or %v for a version number. So it's a pretty convenient interface actually, and you can add quite a lot of different data there. Okay, so once we have our region annotations and our metadata, you can run a program with the Caliper spot config. The spot config also accepts a lot of different additional options, like, for example, MPI profiling if you want it in your spot output. And once that's done, it produces a .cali file, which contains all this profiling information. And you can move that into a directory and load it in the spot web interface. And we'll look into the web interface a lot more in, well, just a few minutes. Okay. This part I can actually do somewhat live. What in the world is that? Let me move up. Let's see that. Oops. Just trying to move the zoom control somewhere else, but I'm not too successful. Anyway, so here we are in an installation of this Caliper tutorial repository that I showed you earlier. And we actually put a link in the Zoom chat and also in the Hoover app if you want to play around with this yourself. But you'll find here Caliper, RDAC, and a bunch of example applications, namely Lulash and Access Bench. And all of these are prepared and instrumented with both RDAC and Caliper, and you can play around with those. So let's take a look at the instrumentation that we added to Lulash first. So in Lulash, we are mostly actually instrumenting functions. So we're using this Cali CXX mark function macro, which will just, well, instrument this particular function. In the C++ case, you only need to put it at the top, and Caliper will take care of everything. Now, we didn't actually instrument all the functions, just the top level ones. And this is, again, to reduce overheads and clutter that you would get by just instrumenting everything. So in addition, we also added metadata annotations with RDAC. That is in Lulash util. So there's a new function in here, record globals, and that adds all our RDAC metadata flags. So we first use RDAC's built-in functions to record some of the common information, and then we essentially add these key value results here, or these key values, which record all the Lulash specific information that we get from the input problem. So the number of iterations that we use, the problem size, and other things that you can tweak in Lulash. We also record build information. The way we did that is actually somewhat interesting. So we have a a template file that's filled out by the CMake program, which you can see here. So it will put in the compiler name, compiler version, and so on. And then we just add that to our RDAC values. We also record a figure of merit at the end, but I'm not entirely sure anymore where we do that. But well, it's somewhere at the program exit. And we also in Lulesh have the config manager API. So we actually added an additional command line parameter to Lulesh, and that is what we're feeding to the config manager, so we can control profiling in Lulesh from the through a command line argument in Lulesh. Okay, so let's just give this a try. So actually run the setup script. It should, if you haven't built anything already, build all the example applications and Caliper and RDAC and so on. And now we can play around with them. So first of all, if we just like run Lulesh, I'm just giving it 10 iterations, so it runs pretty fast. It doesn't really do much. We need to add a Caliper configurations. We can use do that with the Caliper config variable, for example. And if we use the runtime report, it will now prints the runtime report on screen. In the serial configuration, we just get the exclusive and inclusive time that we spend in each region. So the time for main is essentially the total time of the program. That would be 0.49 seconds, which kind of matches what Lulesh itself reports. Well, calipers are a bit outside that, so we're measuring more time than Lulesh on its own. And over here you have the percentage of time, so you can see which are the regions that we spend most of our time in, and it's this, well, calc hourglass control for elements here for the most part. Okay, so there are a bunch of options for the runtime report. We can actually print the metadata that we collect with RDAC also. And now it prints that here. Other things we can do is add additional metrics. An easy one would be the region count. So we can see how many times we called each of our functions. And well, for the most part, it's like 10, which kind of makes sense because we use 10 iterations. And some of the functions were called more often than that inside inner loops here. Okay. So let's see, in addition to the, well, I can also show you the Cali query program. So if you want to know which flags are available for a specific config, you can say help runtime config, for example. And, oops, and well, then you see all the different configuration options that are available. So not all of them are actually available in this particular build. So some of them require additional build options. But this would be available if you enabled every single Caliper configuration flag at build time. Okay, so what else can we do? So as I mentioned, we have the config manager API, so we can actually use a command line flag here, the -p runtime report or the -p flag with a Caliper configuration, and now we can control profiling as a command line argument theoretically. Oops. We'll do that, of course. Now, to record data for Hatchet, as I mentioned, there are a lot of different options. We can use the Hatchet region profile configuration. And that will add this region profile JSON file, which you can load into Hatchet. But we're talking about Hatchet in just a bit. Now, finally, for Spot, we're using the spot config, and with that you can set up all kinds of automated processes. For example, you can just collect a whole bunch of different profile files. If, for example, we want to create a study of different input flags, we could run lulash a couple different times with different problem sizes. Use the spot config to record profiling data for spot. And that will produce a couple different .cali files, which we can actually look into with the Cali query program also. And well, the contents of the spot profiles are actually quite similar to what you see with the runtime report. So it records the time you spend in each annotated region, and in an API program, it reports the minimum, maximum, and average, and total amount of time that you spend in there. Okay, so are there any questions so far? If not, I will go over and show a quick demo of Spot itself.
We did just have a question come in. Does Caliper support multi-threaded applications, such as measuring OpenMP tasks inside a parallel region?
It does. So it definitely supports multi-threaded applications. There is some specific support for OpenMP as well. So you can enable the OpenMP tools interface, and then it can tell you additional information about threads and parallel regions and so on. Okay. In that case, let me show you a quick demo of Spot. So let's quickly go back to my slides, skip this. So when you actually find Spot, so if you happen to be a Livermore LC user, you can find a local installation there. So it's running on our own system, and you can reach it onto that URL. If you're not a LC user, there is a container available, so you can build your own Docker container with Spot running in it, and then use that. So it's unfortunately not the most convenient thing to create and run Spot at the moment, and I can't really go into much detail in this tutorial here, but if you're interested in running it locally on your site, just drop me or Matt Legendre an email. I can, yeah, hopefully help you out. But assuming you are able to run Spots, this is what you would see. So you can load Spot through the container or this aforementioned URL on an LC system. And then you see a, well, actually you don't see this particular thing. We already loaded a data set that you can do here in this top level corner. And well, this is a relatively large data set, and it's going to take a couple of seconds for Spot to load it. But let's see. And it will then essentially show you various widgets with the metadata for an experiment or for a set that you have selected. So essentially it loads all the profile data sets that you have in this particular directory that you specified here, and then you can go through them. So you can customize this view by clicking on all these different, or you can enable and disable all the different widgets which represent all the RDAG values that we collected with our program. And in the experiment here, let's pick a couple different things. So we can choose the compiler. The figure of merit is always nice. Your job size might be interesting. Your problem size is interesting. You don't actually need the user because there was only one in this data set. And do we need anything else? Yeah, threads would be interesting. Okay. So you can select widgets for each of the RDAC metadata values that you had in your program. And now it shows, or now Spot shows them to you on this front page. So what they are actually histograms. So all of these widgets show you how many runs you had with a specific value of your metadata. So for example, there were about, well, what is it, 650-ish runs with the problem size 30, and maybe like 250-ish runs with 16 threads and so on. And these widgets are interactive, so we can, for example, select only the runs with the largest problem size here, and then all the other widgets will adjust and show you only the subset or this specific subset of data. You can actually use that for some simple performance analyses. So for example, we can select this larger figure of merit here, which represents the overall performance that we had in our Lulash runs. And we find that for this large problem size, most of these higher figure of merits came with the glue compiler and, well, like a medium amount of threads. So let's reset this here. So if you scroll down, we actually have a table that shows all of the runs that we have selected. So currently, because we selected this problem size here, we've selected 250 out of our 924 total records. There are 2 buttons here. So this time thing actually brings up a separate page, and that shows you detailed information for this particular run. And but it shows you all the metadata values that we collected, and then all the performance metrics, and a flame graph profile of all the annotated Caliper regions with the minimum time per rank, maximum time per rank, and the total time in the entire program. But that's not, oh man. These zoom controls are kind of annoying, to be honest. Somewhere else. Let's go back here. So that is, however, not what we usually do with Spot. So we don't often just look at a single run, but instead we want to compare many different runs, and we have pretty powerful tools to do that. So let's focus for now just on the runs with 16 threads. And then we can look at this compare page here. And this shows us essentially a timeline, in this case, of all the runs that we have. And we can configure this in quite a lot of ways. So for example, we can group these timelines by various things. So for example, we can group them by a compiler. And then you can compare performance between all the different compilers. So we have the GNU compiler up here, separate graph for Clang down here, and another graph for the Intel compiler down here. So you can see how performance evolves over time. And apparently there was a little bit of a bug here. So performance all of a sudden varies quite a lot and got a little bit worse. So we can actually click in here. So the color of these things actually represents Caliper regions. And now we see the time that we spend in the time increment region plus the Lagrange leapfrog region in this view down here. And this also adapts to all the different graphs that we have here. So you can really dive into this program and figure out where some specific performance issue happened. Oops. As we scroll along here, you also see that we can select the individual runs for each of these events. It shows us, again, the metadata for these runs and the entire Caliper region profile. This is also actually quite a bit more adaptable. So instead of the launch date, for example, we can use this to create a scaling study. So for example, we can put the number of threads on the x-axis and say the average time per rank. and use an aggregation for all the similar values like averages. And now we all of a sudden have a scaling plot, so we can compare how performance varies between 8, 16, and 32 threads. And since this is actually I think it's a strong, well, it should be a weak scaling problem. So we see this is actually pretty terrible in this case, because we would expect this time to stay constant. But overall, I hope it goes to show you what you can do with Spot. One thing I actually haven't showed you, you can launch Jupyter notebooks directly through Spot. So there are two ways actually. So you can look at individual runs in the table here, or you can actually create a single Jupyter notebook with a whole lot of runs and compare those. Let's, for example, select just the runs from the latest launch date. Let's brought them down to about 9. We can hit this button, and this should bring up a Jupyter notebook, which uses a template that already imports Hatchet and loads all of the runs that you specified in the selection in Spot. And in this case, well, uses Hatchet to show you all the data, and you can then do all kinds of computations with it. That Stephanie is going to tell you about in a moment. Okay. So I think I'll leave it at that in the Spot demo, unless there are any more questions. And if not, I think I'll hand over to Stephanie. Is that okay with you?
Yeah, that's fine. There is one more question quickly is, can you define again what is figure of merit here in this plot?
That is a specific figure that's defined by Lulesh and essentially tells you, well, the work per time it did. So it's a Lulesh specific figure that, well, tells you how much you did and how well you performed. Mm-hmm. I'm not entirely sure how it's defined, but you would find it in the Lulesh source code somewhere.
Perfect. Thank you. Yeah, that's the last question from the chat that I have.
Okay.
Let me share screen. To get this closed. Slideshow. Okay, so let's go to the chat. Okay, so let me go ahead and get started. The first slide, before I jump into an introduction to Hatchet, is how to get our Hatchet tutorial materials. So as David had shown you, we do have a Spot container up on our GitHub that includes a sample notebook with a Hatchet installation and data sets to play with. Again, that can be a little bit cumbersome to spin up. So alternatively, you can access this Jupyter notebook and Lulesh datasets in this Hatchet tutorial directory or Hatchet tutorial GitHub. And this is actually integrated with Binder Hub. And this will spin up a local interactive environment for you to use Jupyter only in that notebook or in that repository. And so following this tutorial, you can substitute your own Spot and Caliper data files into the notebook so you can play around with it with some of the data that you might have locally. And we'll be using, we'll demo this material in a live demo at the end of this presentation. Okay, so revisiting the software stack of tools that David had mentioned for our performance analysis suite that we've developed. David covered these two tools on the left. We have Caliper for measurement and annotation of our codes. We have Spot here in the middle for web visualization. And then we have Hatchet here, which I'll go into, which provides programmatic analysis on the same input files that Spot actually works for or works on, and that's by design. And as David had shown from Spot, you can click on a notebook down or a Saturn icon down at the bottom, and this will pop up a Jupyter notebook where you can perform your Hatchet analysis. So Spot, with Spot, it provides easy access to using Hatchet. And so, in this tutorial, we're focusing on analyzing data in Hatchet that's specifically coming from Caliper annotations and instrumentation. Hatchet can also be used as a standalone performance tool on other types of performance profiles from HPC Toolkit, from Tau, gprof. And we're currently in the works of developing a reader for Ascent in situ visualization data as well. So just showing the web interface from Spot. Down at the bottom of the web page, there's a table of runs where you have a row in each table for the different Caliper files that are in the directory that you've pointed at. And on the right of each of the rows, you've got a Saturn button that will bring up a templated Jupyter notebook for that particular file, so you can load it in. Otherwise, there's a Jupyter button on the outside of that table of runs, which will load in several Caliper files at once for you to do performance analysis. So what is Hatchet? Hatchet is an open source tool to automate analyses of parallel profiles. Using Hatchet, you can use Python to programmatically write scripts and identify bottlenecks in your codes by leveraging the performance data that we're collecting from our different profiling and tracing tools, like Caliper or HPC Toolkit or Tau. And then by having all of this performance data and being able to use Hatchet, we can gain some insight and learn where our code is spending its time. We can use Hatchet to subselect a region of the parallel profile, and then you can filter and focus on a particular region. We can compare across multiple execution profiles, and we can, again, use Python to write scripts and automate this analysis in notebooks or just in a Python script. So what info do we collect from these different profiling tools? The data can be stored in either a calling context tree or in a call graph, which is showing the information about which node calls other nodes. So in this example, we have Foo calls Waldo, calls Garpley. And then each node in the tree might also have contextual or function level data depending on what profiling tool you're using. So for each node, you might have the file where it occurred, maybe the rank ID. And then for Caliper, you might also be getting the time that it took to run that particular function, but you might also have floating point operations or cache misses to go along with that. And as I mentioned, you can use Hatchet in this Caliper Spot framework that we're discussing today, but you can also use Hatchet outside of that to load in data and perform analyses on profiles from HPC Toolkit, from Tau, from gprof, and PAPI as well. And if you have a different file format that we do not yet support, we're always looking for new contributions. So please feel free to reach out to us if you're interested in having support for that data. So at Hatchet's core, our data structure is called a graph frame. And our graph frame consists of two components, a graph here on the left, which is storing the relationships of the parents and the children. And then the other data structure that we have is a data frame that goes along with that. And this you can think of as a two-dimensional table. In pandas, it's called a data frame, and this is storing all of the metadata that's associated with each node, such as the file where it occurred, maybe the particular rank that called it, how much time it took to run that particular function. And so we can use this node column here in the data frame to map into the graph structure to determine where it is in this graph and determine what is the parent and what is the children of that particular node. So how do we visualize Hatchet's two graph frame components? If you have a variable that you've read in a particular file called GF, which is short for graph frame, Hatchet provides a tree function so that you can print out the call graph or calling context tree of that particular profile here on the left. And you can see by default that each of the nodes is assigned a particular color of the metric that's being displayed. So for this particular example here, we're showing the time metric on each of the nodes, and our nodes with a high time value are highlighted in red, and nodes with a low or a fast time value are highlighted in green. So you can quickly be able to look at your tree representation and have nodes that are of interest kind of jump out at you. And we can also, there's new features in our latest Hatchet release for reversing this tree legend because it might not make sense, as well as providing additional color maps if the red-green is not sufficient. And then the data frame component of the graph frame can be printed out by just doing gf.dataframe, and this will print out using native pandas. So this is the HTML display of that particular data frame. So once you have read data into a Hatchet graph frame, one of the neat features of Hatchet is that you can now compare two graphs or multiple graphs or graph frames, even if the structure of the graphs themselves are different. So if we look here in the upper right, we want to compare this foo bar chord graph to the foo bar has children Baz and Grout graph. So these structures are clearly different. As an example, you can kind of think of this as maybe a serial run compared to an MPI run, and trying to understand how the performance changed as you moved to parallelism. And so what's going to happen under the hood as part of this comparison is first we're going to unify the two trees since the structure is different. And so if we were to unify this left graph with the right graph, we can see what the resulting graph looks like. And once we have that unified graph, then we can perform a variety of different mathematical or arithmetic on these graph frames. And so if we want to do a GF1 over GF2, we can see here is, if we think about this as our serial run, where a node, in this case, bar is contained in both of our graphs, this division is going to do a straight divide of the 6 over 3. And so our resulting bar node here in the GF3 will be a value of 2. And if we look at another set of nodes that are in GF2, such as maybe the MPI nodes that are only contained in your right graph, when we perform this division, we're going to enter in a nan because it says, hey, we can't do this division. And we're going to annotate the nodes in the resulting graph frame to indicate which graph these nodes originated from. So here in this case, our Garpley and our Grout nodes only existed in the right graph. So we indicate that by this green arrow that's pointing to the right. So one of the other operations that we can do in Hatchet is filter the graph frame so that you can focus your analysis on a particular region or area of the graph. So this first filter example is filtering based on the particular node metrics in your data frame. So in this example, we're interested in keeping nodes that have a time value greater than 1. Maybe we have several nodes that are very fast and we're not interested in them. And so we want to remove all of that extra noise from our graph so that when we're printing it, it's only nodes that are of interest to us. So if we take our input graph here on the left, and we're only focusing on nodes that are greater than 1, we'll see that the root node foo disappears. This child nodes QUX also disappears, and we rewire the graph, removing those nodes that are no longer of interest to us. And so you can see the resulting graph here on the right. You can also look for specific patterns in your graph using Hatchet's query language. And so the query language was designed to enable users to filter their graph sizes based on the relational parent and child relationship that we provide on the graph structure. So whereas the previous example was just on a metric value, irregardless of where it fell in the graph, the call path query language allows you to take all of that into account. So we're going to walk through this example here very briefly. But the query here on the left is provided in the form of a list of abstract graph nodes that are used to match nodes in your graph. The nodes you can provide, as shown here as an example, we can provide them as a filter as we used previously. So here we're looking for, in the data frame, a node with a name that matches the word solvers. And we're also looking for a node that matches a time with a time value less than 50. You can also specify nodes using standard regex wildcard symbols. So that's dot or plus symbols or the asterisk to indicate how many nodes that you want to match. So if we use this call path example here on the left, if we were to think about that in a, in true grammar form, we're looking for to match a call path that first has a node with the name solvers, is then followed by a node that has a time value less than 50 seconds. And then we want to match 0 or more nodes underneath that, which essentially takes you down to the most leaf node of this graph. So walking through here, we have the first element in our query. We're looking for this node that has the name solvers. And so we're going to save that to our resulting result graph frame. The next bit that we're looking for is a node that has a time value less than 50. So you can't see that reflected here in the graph, but the MPI node in our case here is the one that matches that particular syntax that we're looking for. And then the last element in our call path query is the asterisk. And so we're wanting to match 0 or more nodes underneath the MPI node. And so that's what gets us the leaf node of PSM2. And so that's how we walk through our call path query language. Oh, let me see. Okay, so jumping back to the Spot webpage, the question is how we can load Spot and Caliper data into Hatchet. So this first figure here is a screenshot of kind of a modified version of the Spot webpage. So at the top, you would have this text field here on the top, where you can enter a directory pointing at Spot and Caliper files or Spot Caliper files. And at the bottom is that table of runs that will populate based on the directory that you've specified. And then again, you've got your Saturn buttons here that you can click on, and that will read in either a single data file or several Cali files into a template notebook so that you can then begin to do Hatchet analyses on them. And with that, I think I will jump to our live demo. And in the meantime, I can answer any questions as I'm doing that, if there are any.
No questions so far.
Okay. Am I sharing my whole screen? I can't remember. Let's see.
Yeah, it is your whole screen.
So you're seeing the Jupyter notebook now?
Yep.
Okay. Can make this a few bigger. Okay, so I've jumped ahead and just brought up the Jupyter notebook, and this is called Hatchet Tutorial Demo, and it's populated with a few different analyses that we can do with Hatchet. And I went ahead and pre-populated or pre-ran all of the cells in my Jupyter notebook. So if you're new to Jupyter, each of these kind of boxes is what we consider a cell. And so we've, you could put all of this code into a single cell, or we typically try to break them up into smaller kind of pieces, so it's easier to follow along. But typically when you just open up a new notebook, none of these numbers will appear on the left. They'll be clear to indicate that you haven't yet run this cell. And again, you can also get this information or this tutorial at our link here. And I don't know where my chat window went. David, if you're able to put that in chat, that would be great.
Yeah, I already did.
Perfect, thank you. So at LLNL/Hatchet tutorial, there's this link here for Binder, and all you need to do is click that and it will start to set up a container or a, I guess, yeah, it sets up a container in Binder Hub to allow you to run the notebooks yourself in a contained environment. And so you'll have a Hatchet installation already there. The Hatchet tutorial demo will be there, as well as some other examples that we've given over the years at different tutorials. So you can either follow along in Binder or I will walk through the notebook here. But the first cell is just doing a bunch of different setup, importing a lot of different modules that we will need to use as part of our tutorial. I think key here is we are setting our Python path to include a Hatchet install or a Hatchet directory, as well as the spotDB directory. And then we can import those, import Hatchet as HT and import spotDB. So the first example we'll walk through is how to load in a single data file and visualize the two graph frame components, that is the tree and the data frame. So we've set here as the input deploy string to be the path to the Caliper file that we're using. So this will be the single Cali file indicates a single run. And then we're using the spotDB module to connect to that data directory. And then from the Hatchet side of things, we can call this from spotDB function and point at that database that we've just set up, as well as the list of Cali files, which we've called runs, is also passed to that spotDB function. And so once you have that, you'll have a list of, well, in this case, it's a single file. But if you were to have multiple Cali files, you'd have a list of graph frames as the result of running this spotDB function. Within these files, you can now use, you can grab particular audio data, such as the launch date or the job size. These are all stored on Hatchet's graph frame. So you can then you can filter your Cali files, if you like, by particular launch date or job size, or any of the other audio metadata that you have access to. So we're just printing that here just as an example. And then when we want to print the tree to the terminal, we can use the gf.tree. And this will show us the Hatchet visualization of our Cali file using what is called the default metric. So in this case, it's our total time inclusive. And you can see that nodes with a higher time value are highlighted in red. And this is inclusive time. So the root node is what's going to have the highest runtime. And then as you walk further down the tree, you'll have nodes gradually become more dark green to indicate that they're at the leaf nodes and have the smallest amount of time, since this is inclusive. If you're ever interested in all the different parameters for Hatchet's tree function, you can use a native Python function call called help. on the tree method. And this will show you all the different parameters that we provide on the tree or on any of our other Hatchet functions that you might be wanting to use. We can display the data frame simply by calling print on gf.dataframe. If you're using Jupyter, it tends to come out a lot nicer if you display it in HTML format so that all of the columns are next to each other, depending on how wide your data frame is. If you were to just use the native print, it might break those columns onto different lines. It makes it a little bit harder to read, but those are that capability. The next example I have is how to filter on the tree. So in this case, we are still looking at a single Cali file that we saw above. And what we're doing is wanting to create a new column on this graph or on this data frame that can translate the total time inclusive into a percentage of the maximum. So it's a more accurate representation of functions that are consuming a lot of your overall time than the total time inclusive metric. So we create a new variable where we get the max time over this total inclusive time column. And then we create a new column on our data frame called PCT of max. And we just take that, take all of the values in the total time and divide it by the max time to get that percentage. So obviously our root node main is going to have the highest percentage, and you can see it start to decrease as you walk to the other nodes in this data frame. So now we want to filter our tree to only contain those nodes that consume at least 60% of the maximum time. So we're going to apply a filter function onto that new PCT of max column, focusing on those nodes that are greater than 0.6. And then we can call Hatchet, Hatchet's filter function, gf.filter, using this filter function that we have defined. And you also see that there's the squash equal true parameter as part of the filter function. Filter by default will squash the tree. If for some reason you only wanted to filter the graph frame and not affect the input graph, so that is this structure. If you wanted this to stay the same and just perform a filter for whatever reason, you can pass squash equal false. What's happening if we do squash equals true, we're not only removing the nodes out of the data frame, but we're also going to rewire this graph to match what's left in the data frame. So as a quick way to, once you've performed that filter, we can perform a call the len function on each of our graphs to simply count how many nodes are left in the graphs. And so you can quickly see that, you know, my input had 19 nodes. And then by performing this filter function, looking at nodes that contain more than 60, or that consume more than 60% of the maximum time, we can see that the resulting graph now has 4 nodes. And so if we were to print our resulting tree, here now on our filtered squash GF graph frame, and we've changed the metric that's being printed on the tree to be the PCT of max, we can see that these are the remaining 4 nodes that satisfied what our filter function was asking for. Okay, so those 2 examples looked at a single Cali file. Now we're going to walk through an example of looking across multiple Caliper files. So this first example is looking at the percent change over nightly test runs. So you might have an application that you're running several times a day or once a month, and you're interested in understanding what is the performance change over time for the particular application. So in this case, we have a list of 2 Cali files generated, let's say yesterday and today. We read those into Hatchet using the from spot db function. And now we've got 2 variables here that we've defined that contain either the first element of our list of graph frames or the first element. And then we can perform a percent change over time. So we take, percent change over some denominator or standard that you've defined. And so once we do this percent change, we decided that, hey, we would like to scale the particular resulting column by 100. So we've got it in a percent instead of in a decimal. In our next stage, we want to add a new column that takes the absolute value of our percent change, since we don't take that into account in our original arithmetic operator. And so we take the absolute value here and store that as a new column on our graph frame. And then we can use that column to print the values on our tree. And so if you take a scan through this tree, we can see that, hey, the MPI com split highlighted in red here indicated a high percent change over time. And, maybe this was due to, a change in the MPI version, or it could be due to network noise. You can also see that MPI barrier also had a particular high percent change over the two files. And so, looking at this tree, this might be a good indicator into where to start looking at why those changes occurred. So here we're printing the data frame component of that, of course. So I'll quickly scan through that. So we had talked about why, or highlighting that, hey, this MPI node had a high percent change over time. We might be interested in understanding or analyzing why that might have happened. So we can perform further analysis in Hatchet to filter our graph frame by the MPI nodes and the non-MPI nodes to further determine, is the change coming from the MPI part of my application or the computation side of my application. So first, what we're going to do is create a filter that only looks or only contains the MPI nodes. And so we're going to define our filter function here, matching any name that starts with MPI underscore. And we're going to apply the filter function to have a graph frame that only contains the MPI nodes. And here we're just printing out the data frame component of this, but you can see that the data frame here only contains all of our MPI nodes from the application. And then we're using Python here just to calculate the average percent change over the MPI functions. So we can say we have a pretty high percent change over MPI of 19%. We can also create a filter to extract the computation side of our application. So whereas before we were looking for, we were trying to match names that started with MPI, this particular filter function is going to match everything else that is not the MPI functions. And so when we display this data frame and calculate the average percent change, we can see that our computation side only had a change of 1.6. So we can start to deduce that, hey, maybe there was a big network interference that caused a severe change in the MPI communication. And our last example is to calculate the speed up between two trees. This was the example that I had walked through earlier in the slides. But in this case, we're reading into files that are run across different job sizes. So we've got one at 1 rank and another Cali file at 64 ranks. We are displaying here the two trees. So here's our 1 rank. And here is our 64 rank. And of course, you can now see that this graph structure is clearly different because we now have the MPI functions included in the tree. And so when we go ahead and compute the speed up of going from 1 to 64 ranks and print that tree, you can see that we're getting nans because it wasn't able to do that division. And then you've got the annotations on each node to indicate that, hey, this came from the rightmost tree, which was our 64 node tree. And then you can see that, maybe because I'm doing speed up, that the red highlighting of, nodes with high speed up doesn't make sense. And so on the tree function, we provide an invert color map so that you can invert the color scheme. And so you can have red nodes highlight the nodes that have poor scaling or, low values in this case. And so these are obviously a very small, these are particularly small in terms of the actual time of the speed up, but we could increase the level of precision to help us, be able to hone where it is that we're focusing our analysis on. And then here's the data frame that goes along with it. And you'll see when you do as part of the union, you'll see a new column on your data frame or on your resulting data frame called missing node. This is just how Hatchet's using this internally to do the annotations of the right green arrows or the left red arrows. That's all that the column is being used for. Oh, sorry, I've got one more example. So this last example is generating a scaling plot over 5 different Cali files. So we've got a set of 5 Cali files ranging across different job sizes. We're actually using matplotlib and standard Python commands to manipulate the data into a particular table format that we need, such that we can then make a plot of our data focusing on a particular function. Where did that go? Yeah, so this for loop over here is iterating over our 5 Cali files. We're getting the number of ranks that the particular Cali file was generated on, and then we're applying a filter function because we only want our plot to focus on the calc functions that have a particular runtime. And then we can apply a bunch of labels and legends, and as a result, be able to quickly produce various scaling plots that you can use in your reporting or in different presentations. Okay, any questions on the notebook?
Don't see any in the chat yet.
Then I'll jump back and we can wrap up and then we can open up for questions.
Sounds good.
Okay. So quickly to review various topics that we covered in the Hatchet part of the tutorial, we looked at how to load in a single data file from Spot and Caliper in particular, using the from spot db function in Hatchet. And looked at how we can visualize the tree and the data frame component and be able to filter and squash the tree, either using the node metrics on the data frame or using the query language to take into account the relationship between parent and children. Other examples that we walked through was subtracting 2 trees, calculating the speed up of 2 trees, how to add new columns to the data frame, which of course is a standard Python command, is not necessarily specific to Hatchet, but can be used to enable different Hatchet analyses. And we also looked at how you can manipulate a Hatchet graph frame or several Hatchet graph frames to generate speed up plots that you can script over and be able to produce several different times, iterating over different sets of Cali files. Other features that we weren't able to cover in today's tutorial, there's a group by an aggregate function so that you can change how the graph and the data frame are set up. So by default, we typically are grouping by on the node, but you can group by and filter other node metrics such as the file or the function name if you want to transition from a calling context tree to a call graph. So these are other functions that you can look at and use. And then you can always, of course, reference our user guide for the wide variety of different analyses that you can do. And there's some example analyses there as well that we weren't able to get to in today's tutorial. So just in summary, we have Hatchet, which is a performance analysis tool for parallel profiles, and it enables you to script your analysis of hierarchical data from one or several different parallel profiles. As some of our future work, we're working to support other profile formats by adding new readers, and we welcome contributions from the community to help us support that. We're also looking at a way to output our graph frames to disks because we're starting to try to read in larger and larger profiles and want to avoid needing to start over from scratch each time we come back to it. We're also working on a higher level API to do a lot of this general examples that folks have been asking for, so that will kind of reduce the number of lines of code that you need to write to a single function that can do these particular things, such as speed up, as an example. And with that, that ends the Hatchet tutorial part.
Okay, great. Thanks, Stephanie. So I think we have like 2 minutes for questions. So if anyone wants to ask a question about Caliper, Hatchet, Spot, feel free.
I don't know how to stop sharing my screen. Am I still sharing a screen?
Yep.
Well. Stop share.
Okay, well, otherwise, thank you for joining. So if you want to try out Caliper and Hatchet yourself, so we put these links to the tutorial materials in the chat. So you can find them there, and we can also put them on the Uber app, I think.